Good afternoon, everybody, and welcome to the AI ML for Food and Beverage webinar. In the next hour, we'll try to unravel the promising myths of artificial intelligence and machine learning, terms which are quite popular these days for you. And although the subtitle says for food and beverage, you will see that the use cases we picked actually are adaptable for other industry sectors as well. So welcome everybody. My name is Kees Lambregts and I will host this webinar together with my colleague Cameron Bolt. Now let's have a look at the agenda. I'd like to start with a short introduction who we are as Novotek, and then from that point we'll jump right into the main portion of this webinar, the data analytics. Some background information, but most of the time we will look at practical use cases, and we try to build use cases around different kinds of aspects of data analytics, namely machine learning, as you can see, principal component analysis, and advanced process control. At the end, we'll give you some hints and options actually how you can start your own analytics journey with tools and help from us provided if needed. So who is Novotek? Novotek delivers solutions in industrial automation for both OT and IT, and we have done so for almost 40 years now. As you can see, we are active in most Northern European countries with a headquarter in Malmö in Sweden. In total, we have almost 200 specialist experts in all fields actually of industrial automation to help our customers optimize and improve their production processes. Our mission is therefore helping manufacturers to accelerate in their digital transformation journey. How do we do that? We are active actually in almost all layers of the traditional industrial automation hierarchy, as you can see. So all the way down from control through OPC data disclosure, SCADA automation, HMI systems, manufacturing execution systems. But the main topic of this session will obviously be analytics. We see a lot of our customers struggling or challenging with the digital transformation. And for that, actually, we define certain steps you can follow in order to grow in that transformation phase. In fact, it all starts with connectivity. First of all, you need to digitize your data and make connection to the machines, the assets, the sensors that you have in your production environment. Once those signals are available, we also recommend to model that, to unify, to make the data available in objects for the IT applications. Data storage is important, different kinds of data, as we will see, in particular for analytics purposes. We are dealing with time series data and event-based data. Visualization is important, both real-time and also for analytics, including dashboarding. And the last step of course, is optimization. Optimization, which is the main goal of data analytics. What we see in data analytics is that the usage of a model is very common. A model is a simplified representation of the reality. We use models in order to be able to perform testing and prediction. As you can see in the example here, we could easily test in the model how the house would look like if we paint the garage door in another color, or even more complex if we add another room in the construction. Such tests would be more difficult in reality. And the same is true actually in production environments. Well, we think in systems, and we try to create models actually to represent the real system behavior. As you will see, there is a variety of different models available in this webinar. Today, we hear a lot about large language models being used in ChatGPT. But for process optimization, we will still focus mostly on analytical models. Question is how to build such a model. Most of customers already have a lot of data available these days. And as I said, varying for real-time data through historical data, relational data, and typically you use an analysis tool actually to build actually your model. Once you have your model built, you can connect this to the real-time data, and out of that connection, you can do some predictions. And these predictions can help you to optimize your production process. The analysis tool you will see in the use cases presented in this webinar is called Proficy CSense, which is a commercial available analytic package from GE, General Electric. I will tell you some more about that at the end of this webinar. As we see, it all starts with data. So data needs to be well prepared. Good data is key to build a good model. First, we need to prepare this data. It starts, as we saw in the digitization cycle, with collecting the data. As a metaphor, you can imagine different kinds of Lego building blocks in different colors and different sizes available in your box. But how are you going to build actually your model at the very bottom? You need to sort the data, you need to organize it, you need to learn from it, and then you can, following the descriptions typically in the manual, you can build your model. In data analytics, we do the same. We collect and integrate production data from sensors and PLCs. Next, we sort and standardize the production data. Think of different engineering units, different sample frequencies. It all needs to be synchronized, different data sources to make it useful and comparable. Then organizing your data in such a way that other systems can easily have access to it for purpose of reporting, trending, and analytics. Visualization helps you to better understand what information is hidden in your process data. You will see some nice examples in this webinar with scatter plots and how you can better understand actually the behavior of your process by visualizing your data in different ways. And the last step, you build the model, but that's actually, once you have done the previous steps in a good way, is the most easy way actually. Which brings us to the first use case, and that focuses on machine learning. Machine learning is a part of artificial intelligence that aims to build a model. As you can see in the graph here, there are several types of machine learning. In this first use case, we'll focus on supervised learning. In supervised learning, you try to develop a predictive model based on both input and output data, which means that you present actually the input signals and the output result from the reality to the training program. As you can see, there's a difference between classification and regression. It's explained in this slide. On the left, you see with classification, we try to distinguish between two or more different groups. While with regression, we try to establish the relationship between two or more variables. A model, as you can see in the simplest form, can be just a linear relationship. And with this relationship established, it's easy to predict, in this example, how many patients there will be with a certain amount of gene, as you see on the x-axis. And that's typically what we do with modeling. In this example, we're about to see, we will use decision tree modeling. And in decision tree modeling, we built the decision tree in order to distinguish between the green population dots and the red population dots. How do we do that? The trick is actually to establish the optimal borders to separate these two groups. The system, of course, helps you with that. Here, the borders are indicated by the yellow lines in the diagram on the left. On the right, you see the nodes which split actually the population into two groups with the highest entropy. The aim is actually to end up with the end nodes, as you can see, which all result in 100% of one population, either the red or the green. With this decision model established, it's easy once a new node, a new coordinate, like you see here, 15,7 arrives, we can just follow actually the nodes and see here the first 15 is larger than minus 12. 15 is also larger than 9, which ends up in a final node and says this has to be a red dot. That's the background principle. And of course, in reality, things might be a little bit more complex, if not only for the fact that there are a lot more variables involved, but the principle remains the same. The first use case brings us to a packaging line. There are a lot of challenges in packaging, of course. And one of the challenges is the weight that we package. If we give too much weight, if we put too much weight in each package, that is called actually, then we are obliged to, that is called giveaway. And giveaway is actually free product to the consumer. So that's an easy business opportunity to calculate here. In this example, we'll look at batches coming out of a process. And during that process, there is a time series database recorded in a historian with several values, temperature, density, and pressure, which at the end might influence the percentage of giveaway of each batch on the packaging lines. Those giveaway percentages have been recorded in a separate limb system. And as you will see in the demonstration, are then identified as an overfill, too much product, a good product, or an underfill product. And that brings me to my colleague Cameron, who will show you how this example can be challenged.
So good afternoon, everyone, and welcome. My name is Cameron Bolt, and I know what most of you are probably wondering. And the answer is no, I'm not related to Usain Bolt, and I'm not going to be running anytime soon. But what I will be doing is illustrating to you 3 different use cases in Proficy CSense. So Proficy CSense, as Kees mentioned, is designed to facilitate the user through each step in the conventional machine learning workflow, from data ingestion to manipulation to visualization and statistical summaries, and then to visualization, model building, and then eventually validation and deployment. So in a production process, and very typically of OT data, the sources of these data come from different parts of the process at different times and at different rates. A very typical scenario is one where we have a process, and in the case of a packaging process, where we are producing real-time data. We are measuring temperatures, pressures, flow rates on a second-to-second basis, and this is being recorded in a historian. Then at some later point in time, maybe hours, days, for example, the quality department from the same company will randomly sample different products that have been produced on the line and assesses these products based on standard metrics that are defined internally. And it is precisely this disparity in time that is the first challenge. How does one take the quality metrics associated with a specific product at a specific point in time and associate that with the conditions on the plant at the time the product was being produced? So put simply, the goal is to determine what operating conditions result either in a good product or a bad product. And in this case, a bad product is a product that is overfilled or perhaps underfilled. And the second challenge that one faces, which is more of a practical issue, is how do we combine these different data types? We have numeric data types as well as categorical data types. And we also need to analyze these two different data types with a single sort of approach. And as you might have already figured out, we'll be using the decision tree for that. So what you're looking at the moment is Proficy CSense. And one of the tools available to us is the discrete and batch troubleshooter. So the discrete and batch troubleshooter is one of the tools available. And you'll see a few different ones in this demonstration or in the other demos as well. But just to give you a little bit of a exposure before we move into the actual tool, you'll see there's a few different ribbons. And on the left-hand side, we have a project explorer, which allows you to move through the project easily. We are currently in the data recipe window, which is the first step in a machine learning project, pulling in data and manipulating that data. And then we have different tools available to us or functions that we can use to manipulate this data. So in this packaging process, we have data from a LIMS database, which we can pull in and observe in a very easy way. We can see that each batch is associated with a batch ID, and we have different quality metrics associated with that. And what we are specifically trying to determine is when is something an underfill or an overfill. And in this case, we don't have that much data. We've kept it relatively simple for this demonstration. But we also have real-time data, which is historized in the plant. All right. So we have temperatures, pressures, flow rates, and that is recorded on a second-to-second basis. Here you can see that the delta is only 1 second, and we have an associated batch ID. So we can combine this data into a relational database, and we can aggregate and downsample the data to the batch level, and then we finally end up with this final data set which we can analyze. All right, so we can analyze it, and we load that into our system. And then we move into the first step of this analysis procedure. So one of the things that many people will do, and many of you will be familiar with from an OT background, is that what we try and do is we try and analyze the data as a first step by looking at the graphs of the data. What does the data look like over time, right? And what many of you will have experienced at some point in time is that it is not particularly easy to determine from a graph, especially as we scale in time and the number of variables to determine what is the contributing factor to a specific issue. What caused this issue on my plant? And that is precisely where we get tools like a decision tree to help us or identify and summarize this information for us in a very helpful way. So here we can see we have this graph. We're trying to determine what causes these peaks in the total batch giveaway, right? So we can then move on to the modeling stage, where we're actually going to be using the decision tree for an analytical purpose instead of a predictive purpose, meaning that we're not going to deploy a model at this point in time. We're trying to use the model to help us to determine what are the issues on our plant. So we can build a model and a decision tree model in this case. You'll notice that the different features are already selected for me, but I'm trying to select the different input fields, which is my continuous data, which was historized from the plant. This is our process conditions. And then we are trying to predict the giveaway state, which is either an overfill or an underfill condition. So a decision tree is a very popular machine learning method for the purposes of analyzing data because it is interpretable, as Kees showed us, and it visually maps the decision-making process in a way that is easy to follow. So each branch in the tree represents a decision point, splitting the data based on specific features or conditions. Additionally, decision trees handle both categorical and numerical data, which was one of the problems that we said that we had. So this is ideal for our scenario, right? So we move through into the model building stage. You'll see that we get a nice little block, which gives us a summary of our data. We have 29 rows, not that much. We have 4 overfill rows, 1 underfill row, and then 24 good rows, right? We're going to create a child node, and we automatically are given the option to select which feature we would like to split our data based on, and that is ranked from 1 to last based on the feature which creates the greatest segregation. So in this case, we'll automatically go with the best option, and you'll notice that the full head temperature is selected as the value which segregates the best, right? And you'll notice that we've effectively split our overfill and our underfill tags. and we can continue to drill down until we reach just one of these identifications. So in this case, you'll see we've correctly identified the giveaway state is overfill, and we've segmented that that identification. We now have a set of separations which allow us to predict the overfill state. So what we can now do is almost tell a story. So we can say that if the fill head temperature is above 796.44, and then a very close temperature to that above 797, we expect that we might have some overfill conditions. So a very important thing to do in this instance is to look at the data and the analysis that is produced and try and tell or determine from this whether this makes sense from a physical perspective. Does a critical temperature above a certain value mean that we have changes in density? And can that possibly influence the way that we are filling our packages? So we can do this at a later point in time, maybe from experience, but what we can definitely do at this point in time as a start is move into our graphs and go and check this for ourselves. So we can plot all of these different things together, and then we can see whether this identification makes sense, right? So here we can see that our overfill state is also plotted as these bars. We have our total batch giveaway, which shows a peak. And then we also have our fill temperature up average, which shows a very nice correlation with these different peaks, right? So what we've effectively done is very quickly identified a variable which might be contributing to overfill in our process. Yeah, that's use case one.
All right, thank you, Cameron. And that brings us to the second use case, which is around the technique called principal component analysis. As we've seen in the first use case, we used a supervised learning technique of machine learning, mainly because the output, whether the batch was in overfill, good or underfill, was known. But what if we don't know actually the output? So we want to group and interpret our data based only on the input data and see if we can identify some clusters, some groups of data, and see if the process might become unstable because the data points are drifting from the group. In order to visualize that, show you this diagram, because the challenge in process automation is often that we have so many input tags, process measurements, variables, which influence the reality of the system. So what principal component analysis does is to group together actually these multiple process parameters into a couple of axes, as you can see, which extracts the most actually information against the entropy of the data. So that in this case with 3 axes in the 3D is easy to visualize, of course, but can be multiple axes. You can literally see actually the segregation of the 2 different groups, the red and the blue in this case. That technique we'll adopt in our second use case, which is a story about the bottling line, and in particular about the blade cutter. The blade cutter is a machine in a bottling line with a sharp blade actually, which separates the plastic foils actually that is needed to wrap the bottles. You can imagine at a certain point this blade becomes unsharp or worn, as Cameron will show in his data analysis, and the quality actually of the wraps start to degrade. That's a moment we try to overcome by indicating that the blade becomes unsharp and that it can be replaced actually at a convenient point in time. So for this, we consume actually a lot of inputs from the actual system, the blade cutter. We use that data for training into a PCA, principal component analysis model. It's also called fingerprinting. to get a condensed fingerprint actually of the behavior of the blade cutter. And with that information, we try to predict actually the moment in time when the blade becomes unsharp. I'll bring it back to you, Cameron.
Okay. So once again, we are back in the data recipe stage of our project, which is where we always start with a machine learning project. And as Kees mentioned, we're now moving from a supervised learning technique to an unsupervised machine learning technique known as principal component analysis. So you'll see here that we have different data sets which have been imported, and I've designated them as new blade, new blade, and new blade. And similarly, we have 3 data sets for a worn blade. And this is because we have data from a blade from 3 different moments in time for a case where we know where the blade is new, and for the case when we know the blade is definitely worn. So the entire objective of this analysis will be to determine whether we can define a framework and define this fingerprint, which is indeed characteristic of the new blade, right? And then what we would like to do and hope to see is a visual deviation and a visual degradation of the data over time to indicate to us that our framework is correct. We can actually predict and infer whether a blade is degrading in health over time. So similar to last time, we're pulling in different data sets, we're aggregating them and combining them, and we eventually end up with a data set which combines information about new and worn blades. All right, so we can load this data in. And very similar to last time, we end up with our data summary page. This is all the tags associated with the operation of the blade itself, such as the speed of the blade, the position, etc. And one of the very convenient tools that we have available to us in Proficy CSense is that we can aggregate different batches based on a discrete category, right? So we can do this. We can group all of our data together, and we can see that we have 6,144 rows of a new blade and exactly the same amount for a worn blade. And we can highlight this information. We can say, I would like to brush all of these rows associated with the new blade. And you'll see why this is especially convenient in a few moments, but this is also really nice from a visualization perspective. We can then move into the visualization and determine or very visually see where the difference in the new and the old blade is. So once again, we can try and do this with our eye and determine what is the contributing factor between all of these tags, which will help us to determine whether a blade is new or old, and that can become especially difficult. In this case, we have some noisy data, which is not really that easy to interpret. So we will be using the principal component analysis model. All right. So principal component analysis is especially appropriate for this use case, and it is used very commonly in industry for this purpose, to try and determine whether a specific piece of equipment is degrading or behaving in an abnormal way from the way that it normally behaves. So it reduces the complexity of our multivariate data and our system, right? Highlighting the main sources of variance and potential degradation patterns which may occur. So by building this principal component analysis model, we are effectively, and you heard this term before, taking a fingerprint of the system. And the reason for that is, you'll see in a moment, it looks like a fingerprint. So we're going to use all of our brush data, and this is the data associated just with our new blade, and that's important. We want to build a fingerprint and a definition of our system just for a new blade. So yeah, you can see why we call it a fingerprint. It looks like a fingerprint. We have a projection of all of the data in our system from all of our tags into this new coordinate system. And this new coordinate system is our principal component system. It is a definition or a linear combination of different variables into principal components. In this case, principal component 1, which is designated here as T0, and principal component 2, which is designated as T1. And then on the right-hand side, we have our prediction error plot. And this is very similar in concept to a residual error, which you get when you draw a linear regression line. You can draw a linear regression line through a series of data or through different clouds of data. And every point is not going to exactly line up with that line, right? We have different residual error from that point to the line of best fit. And this is exactly the same concept. These different points show us different points in our data and how it fits against our model. So now what we would like to see and do is see how the data from the old blade looks against this new framework and this new model. So what we will do is easily load in our non-brush data, which is all of our old data, and project this onto exactly the same coordinate system to see whether there's a visual as well as a quantifiable difference. Once we do this, we do definitely see straight away the difference in the colors, yellow and the purple, where the yellow is the data from our new system or our new blade, and the purple from our old blade. On the left-hand side, the first very noticeable thing is that we have a separation into clusters along the x-axis, or this T0 axis. And then we also, in terms of our residual error, have quite a large degradation in terms of prediction error, which is exactly what we want. We want to see this because this gives us a framework to determine if the blade is degrading over time. So one simple way of interpreting this is you'll notice that we have these dashed green and solid green lines, which indicate to us where 95% and 99% confidence intervals are for our new blade data set. So if we take this and say that we know that 99% of our original data fitted below this threshold, anything above this is truly abnormal operation. And we could use this inside our deployment system to flag this. So what we can do to easily deploy this system is move to our modeling summary again, and then back to our rapid process troubleshooting in the top. And you'll see we're guided through this workflow, and we've reached a point where we would like to deploy. We can then deploy this blueprint and then do so like that. And now we'll be moving into a different tool within the Proficy CSense suite, which is the Architect. And the Architect is a development environment which allows us to deploy the solutions that we develop within the troubleshooter. So here you'll notice that we have the same data source that we developed inside the troubleshooter. We have some data cleaning, which filters out abnormal highs and lows. And then we have our PCA model, which we developed. So to quickly demonstrate what we are seeing, we can simulate this model by plotting that process error, that prediction error that we saw previously, as well as another metric known as t-squared, or the Hotelling t-squared metric. It gives you a very similar sort of indication as the distance to the model or the prediction error. And we can now simulate this system in a simulation mode, right? And then we'll be given a visual indication of what this will look like when we actually deploy the system. How will the data be received by us in the SCADA once we actually deploy this? So now we can combine everything and we can do this to fit everything. And here we can see, well, the first thing we see is that we do have a degradation over time in the t-squared especially, as well as the distance to the model. And we have these peaks, which might be a bit strange. But actually what this is when the blade is speeding up and slowing down between different cutting phases, we experience this abnormal or non-linear behavior, right? And that's why it's being highlighted as abnormal. But we're not actually too worried in these peaks. When we want to deploy the system, what we'll be more focused on is the slow degradation over time. So we would filter this on an hour to 2 hour basis and observe over a period of days or weeks how this value slowly increases, and we could alarm it at some critical value like we determined from the 99% confidence interval. And once we are ready to deploy this, we would, for example, pull in OPC sources and sinks, and we would easily be able to deploy this to our SCADA in such a way, right? And that is an indication of how we can deploy the solution. And that's use case 2.
Yeah, so please bear in mind that all you see here, this is a tool for the process engineer to do the analytics on the data. The end result could simply be, as Cameron indicates, a simple indicator on an HMI SCADA screen saying, hey, the blade needs to be changed or not, or like a percentage, how much percent it is worn or not. So all this runs eventually in the background. Right, brings us to the third and last use case. And then we go, of course, one step further towards advanced process control. Because so far we've used the model actually to better understand what's going on in the process, which parameters contribute the most actually to either a quality issue or a preventive maintenance event. Now we see that also this model, once we have that, we can use that to optimize the control system. As you will see, what we try to achieve in process optimization is get a better grip actually on the whole process performance. Each KPI is under influence of variations. And once we have a better grip actually on the behavior of that KPI, we can more closely operate towards the control limits. So that is easily set in a single variable environment. It gets more complex when multiple variables are involved. And that's why we need then systems like data analytics. So the system we're going to watch is steering actually with multiple inputs. It's a multivariable controller, optimizer, MVC. It's providing multiple inputs to the real system in order to optimize the set point of the output. And Cameron's going to compare that with the traditional PID controller, which is obviously a single variable controller. This use case is situated at a pasteurizer machine. And of course, we simplified it a bit, but the principle is the same, that pasteurization is concentrated at a heat exchanger where two fluids actually have interaction with each other, transferring the heat. So we monitor the temperature of the cold fluids and the hot fluids going in, and the temperature of both fluids coming out. And with the set points, actually, we influence, we set the output temp, the desirable output temperature. All the signals are being logged into a historian. And once again, Cameron will demonstrate the advantage of a multivariable controller versus a standard PID controller. Cameron.
Okay. The last demo. So if you're not familiar with model predictive control as a technology, I really urge you to investigate it a little if you're intrigued after this demo. However, what I would like to say about this control technology specifically is that it is not really considered as an official machine learning technology, but it has all the elements of modern machine learning technologies. And long before the craze around machine learning, model predictive control emerged as a closed-loop control technology in the 1970s under the name of dynamic matrix control from Shell. And it has a few elements which make it quite a bit different to PID control, or proportional integral derivative control, which is, of course, the most widely and most popular form of closed-loop control in industry today. So first and foremost, model predictive control is a multivariable control technology with emphasis on the multivariable part, meaning that multiple input variables and multiple output variables are manipulated at the same time. So we manipulate a large set of input variables to control a large set of output variables instead of segmenting them into single PID loops and associating one-to-one, right? And secondly, as the name MPC or model predictive control suggests, we use a model to predict how each of these input variables affect every single output variable. And this means that the interaction between input variables are inherently accounted for, which is something that PID control does not do, right? Which, since it is a single input, single output control strategy. And lastly, the control law itself, where when we talk about the control law, we're talking about how do we actually determine which input should be written back to the plant. And this is an optimization routine, which means that we determine the best set of inputs based on the current information that we have to achieve some objective. And this objective really could be something as simple as, how do I track my set point in the best way possible? All right. So to illustrate what we are talking about and what I'm talking about, we've set up a small simulation. Instead of showing you all the background information or background configuration of how to build these controllers, I thought it would be a lot more valuable to illustrate the differences between MPC and PID. All right, so what you're seeing on the left and right hand side is the model predictive controller as highlighted over here, and the two PID controllers. In this case, we are controlling two temperatures, temperature 1 and its associated set point, and temperature 2 as well as its associated set point. And we have two inputs, input 1 and input 2. And in the PID controller case, we have two PIDs. So we are using input 1 to control temperature 1 and input 2 to control temperature 2. Makes sense. So what we will be doing is making a set point change on both of these controllers, and we're going to illustrate the difference in the way the inputs behave, and we'll see the difference in the outputs as well. So you can see here I have tuning parameters associated with this model predictive controller. Most of these tuning parameters are associated actually with the objective function during optimization. And then we have our very traditional PID tuning parameters, such as the gain, the delay or the reset time, and our derivative, right? So we can now make a change to our set point on temperature 1 and make this 55. And we can update this parameter. Let's update that. There you go. And we're going to update the same temperature on the PID. And then we can go back to our figures and see if that has changed. Yep. So now we can see the MPC responding and the PID responding. And this is meant to look like a SCADA, all right? So that this is exactly how plant personnel would interact with these types of controllers. And this is what they would see and how they would change them. But while these controllers are busy making changes, I'm going to show you on the back end what these solutions look like, and so what we can do is connect to any object that we've deployed within CSense, and we can do this through the architect, which we showed earlier. So we move into the architect, which is where we design our solutions, but when we actually want to deploy our solutions, we move into the runtime manager and we deploy each of these solutions as services. All right, so we can connect to these services. Yeah, you can see I have an MPC running. I have a server to manage the data transfer for the PID as well as the MPC, and then we have our plant and our two different PIDs. And we can connect to this solution which is running live, right? So here you can see I have an OPC source on the front end and an OPC source on the back end. I have my tuning which is being read in, and then I have my controller which is running. And very similarly, we can also observe the deviation of these variables in real time, right? So this is quite a nice feature of CSense, that we can connect to these live objects and train different values which are running through the system. And similarly, as in the case of our PID, you'll notice that the solution looks quite similar, except that we are using a PID block instead of an MPC block. So we can connect here, and we can connect there, and we eventually end up with this, right? Which looks quite similar to what we had before. OPC input and output source, our PID controller over here, and our tuning for our PID controller. So what we'll do now is move back to our graphs to see how the difference in the behavior has been shown, right? So the first thing you'll notice is that the input behavior is very different on the MPC side compared to the PID side. On the MPC side, we see the biggest predominant difference is the difference in the behavior of input 2 as compared to input 2 on the PID side. And the reason for that is that if you look at the set point change, right, besides the fact that the PID is not performing very well at this point in time, the the deviation in temperature 2 is a lot less for the MPC as it is in the case for the PIDs. And the reason for that is that the MPC is taking into consideration the interaction between these different variables and preemptively changing the other input in order to minimize this deviation, while also satisfying the objective of our second temperature loop. As in the case of the PID, and this is one of the biggest differences between PID and MPC, is that the PID will only respond once this deviation starts occurring. So we can see here temperature 2 is beginning to move up as a result of changes in this input 1. And only after that error grows inside of our PID do we see a response in input 2, and slowly this variable is reacting, which is why we see this large error. And we can quantify this error in terms of a rolling relative error, which I'm calculating in real time. And here we can see the relative performance, but rather focus on temperature 2, which might be a variable of specific interest on a plant, such as a pasteurization plant, where we want to make sure that all of our temperatures are stable at all times. And this is exactly what I wanted to illustrate between the two different controllers. It is primarily this control between the different interaction of the different loops. And that's advanced process control in CSense.
Right. Thank you, Cameron. That brings us to the wrap up and end of this webinar. And the question, of course, how can you start your own journey in data analytics? As you see, the tool we've been shown and demonstrated has multiple modules, if I would say. The tool is called Proficy CSense. It's from GE Vernova, where Novotek is the local distributor of. We've seen the troubleshooter in action, which is mainly meant for data preparation, connecting to different data sources, combining the data sources, do some rapid insights, and perform the data modeling in there. Then Cameron also showed the architect. The architect is used to build the end solution in order to connect to incoming data signals and also outgoing data signals. This solution can then be put in runtime to deploy it. And then there is also a web user interface, which was shown actually either to monitor the behavior or to make some configuration changes. So Proficy CSense is a package which is commercially available, but then still you have different choices actually how you can start your own journey and how you can start to work with that. It's possible to fully use this as a self-service tool. There's an online training available. There are demonstration videos on YouTube available to walk you through actually the different aspects of data analytics. Then second, you can also call in the help of our technical expertise, either through an instructor-led training, or you can have a little bit more focus on your own use cases and give some recommendations how to approach these. Then thirdly, it's also possible to call for a complete turnkey project. Once we have a good understanding of the scope, what you would like to achieve, we could also carry that out as a turnkey project. Finally, if you're not sure what this could mean in your environment, with your data, with your production processes, we can also offer you an analytics starter scan, which consists of 3 to 5 days, depending on the size of your plant, the amount of data, use cases you want to have analyzed. We'll have a look at your production data, and we can together actually with your process engineer list potential process improvement use cases. Also, maybe get a bit more insight on the business value of these optimization techniques before you will carry out these projects. In the end, this exercise will give you a document actually with the potential use cases and will also give you a roadmap actually for your own analytics journey. That brings us to the end of this webinar. I see we're well within time, so it leaves us some time for some questions. If there are any questions, please send them in the chat. If not, feel free to reach out either through the mail info.benelux@novotek.com, which you see in the screen. Then I would like to thank you for your time, and hopefully we'll meet each other some other point in time. Have a nice day.